Okay, so today's video is bending potentials. To start with, we have a very basic form which is harmonic potentials. So why do we start with harmonic potentials? Is that let's say you have here, as you see, this C bond H. Definitely there should be two more bonds here, but that's not shown. We just are interested in this motion of bending motion. So if we look into that bending motion, what happens that these are two, one atom here, one atom here, and the other atom in the middle, right? So what happens is that since these are two atoms, when they come closer, they should exhibit some repulsive force, right? And as you go farther away, that should also include some potential. That should add some tension in the system because there are other bonds as well. So you cannot change the configuration or the structure of the bonds too much. So if you change that, if you like they say there was 120 degrees bond angle, right, and change that too much, there would be structural changes in the atom, and that would include some potentials. So to keep that in mind, we start with a potential which exhibit this kind of property that when you actually come closer, that exhibits some potential energy, and when you go farther away, that exhibits some potential energy. So just to keep atoms in a position which is defined to them, but they also have some room for bending. So just to do that, we start with a harmonic potential, which is here like dotted line here. You see, it's written angle harmonic. So as you see, there are four type of potentials mentioned here. All of them are basically bending potentials, or they explain or they describe the bending motion of the bonds. But as you see, the repulsive term looks pretty similar in all the cases with minor differences, right? But on the other side, which is when the angle is increased, all of them actually are different. And the reason being, firstly, I'll start with angle harmonic. That angle harmonic, this harmonic potential is actually not defined after 180 degrees. The reason being because we are using a inverse cosine. So inside this, the value becomes more than 1 or more than minus 1, and that is not defined. So you have to, if you want, you can do it for yourself, because this is basically this theta value is basically calculated from a dot product of the two what do you call, the two bonds. So let's say we have one hydrogen at a, okay, let's do it other way. Let's call it this I. So hydrogen is I, C is J, and H is K. So if we just now look for what is a dot product, so dot product is basically A dot B is equal to AB cos theta, right? So if we do that, here, if I just open a pen, I'm not sure if I can type here, but yeah, I don't think I can type here, but yeah, let's do it with a pen. So if we do that, A dot B, okay, my since I'm writing with a mouse, I think this is terrible, but yeah, just bear with me. So let's say we have A B cos theta, okay, enough. Let's do it somewhere else. Um, okay, so let's do it here. What we have to do is basically, let's say we wanted to do A dot B, right? So the equation for that is the modulus of A and multiplied by, now okay, be let's not complicate this. So modulus of A, modulus into modulus of B into cos theta. So I can just write theta here. So that's the equation, right? So if we want to find what is the theta, firstly we will write cos theta equal to A dot B divided by AB, right? So this one, just remember these two are modulus of individual atoms, sorry, modulus of individual A and modulus of individual B. And now if you want to find theta, what you'll do, you will just put the cos on the other side, which becomes cos inverse, right? So we write it as R cos, and inside that you will write the same thing, AB. So A dot B divided by AB. So that's how you find the theta, and that's exactly what we have done here. So as you can see here, that's exactly the same thing that we did here. The only thing you have to like keep in mind is that if we take the convention I, J, K, because there are like three atoms involved, right? So I, J, K. So the bond direction will always be I to J and then K to J, as you see here, I to J and K to J. So just keep that keep the directional thing in mind, that it will always be from outside to inside. So that, just to because this direction will denote what kind of angles you take, if you take the angles in negative or right. There are other conventions that matters to it, so just keep that in mind when you're doing this dot product. Okay, now coming to the other part, as I've mentioned that the harmonic potential is not defined at 180 because this theta becomes not defined. So that's the problem with the basic harmonic potential. But so there's a big but, because we do use them a lot in many systems, like CH bonds, and other type of bonds that actually do not go to 180 degrees. They can go to 180 degrees, but just think about it, the potential energy is much higher, right? So it is already penalizing. So when I say that it is not defined to 180s, that's why we are not going to use it. You have to think about it, right? So since we also have the potential energy here, just think that if we increase 20-30 degrees, let's say we increase 30 degrees, the potential is about 15 to 13 kilojoules per mole, right? And which is pretty high for just one bond or just one pair of bonds. So we can use harmonic potentials, and we will use harmonic potentials for like 90% of our bonds or systems, but then there are some exceptions for which we will work. So coming to these exceptions, since we have already introduced this part, that at whenever the previous one, which was harmonic potentials, approaches 180 degrees, it tries to go to not defined part. So just to solve that, they have come up with another equation, which is, we are not subtracting the angles itself, but now we are doing subtracting the cosines itself. So that's the minor changes that did, and the form become much natural as well, because now as you see that when we actually put the two atoms closer to each other, the potential energy should actually increase, which is happening in all of the four cases. But when we take them away from each other, there is not enough reason to for the increase of potential energy as we were taking them closer. So when the bending motion happens inwards, the potential energy should be more higher than for the same amount of angle change in the outward direction. So that kind of feature is well captured in this kind of equation, where you subtract cosines directly and not the angles, and take a square of that. So as you see the black line here, so that is actually well preserved, that kind of solution, I would say, and it's well preserved here in the cosine harmonic. The equation form is much similar to the previous one. The way to calculate theta is also same. Here you are not calculating theta anymore, but rather using the same dot product, you are directly calculating the cosine. And now there is also another advantage of using cosine potentials, from rather than just the this directly subtracting theta, is that this one is more faster, because when we are doing simulations, we are not just calculating potentials, but we are also calculating the force and how to calculate the force. So that's like the next chapter. So that's why probably this will be a little new concept to you. But forces are calculated basically by taking a partial derivative of these potentials. So when you take a derivative, it's easier to derive a cosine because as we know, it's just the cosine derivative would be minus sine theta, right? So it's much easier to do the derivative. On the other hand side, once you want to do derivative of this theta, you're actually doing derivative of this large complicated object, which is an inverse of cosine. So that's more difficult for the computer to do it. I mean, computationally. So the time taking for this cos theta derivative is much less, and that's why the overall computational speed also increases when you use this cosine harmonics. Now coming to the third type of bending potential that we use in simulations, and that is restricted bending. So what happens in the restricted bending? So these are the two examples of restricted bending. Is that you are tuning the potential energy, or you're tuning the potential energy function such that the potential energy function can never reach 180. It will be infinite before reaching 180. So in a way, you are avoiding where the where the previous harmonic curve was undefined. So also there's okay, this is a good point. So many people when they talk about mathematical terms, they confuse undefined with infinity, right? Which should not happen. Infinite means there's infinite potential and you can never reach it. Like, right? If I know that if I have to take them closer, there would be a point after which I cannot go because the system doesn't have enough energy, right? Because when we are doing simulations, we are taking energy from the surrounding, right? That's exactly what statistical mechanics explains about these systems, that there would be only some molecules that will be excited because there's not enough energy surrounding us. So once we are doing this bending motion and we know that after this part there is infinite potential, the surrounding will never be able to provide enough energy for this bending motion to happen. So what will happen? We know that only this part is acceptable. So the bending motion will always stay here, which let's do an assumption. Let's say the surrounding can only provide 5 kilojoules per mole of energy for this bending motion. That's kind of a quota that is reserved. Let's say, I'm not saying that's the actual value. I'm saying let's just think about it. So we can actually then put a line here. So I think it's a little higher, but as you can get the idea, that when you actually now do the potential, when you now do the bending motion, you will actually be trapped in this small well, and you will never get to these boundaries. So we do that just to be sure that in any cases it will work. So for example, the restricted bending we cannot apply to linear molecules. So when the molecule is linear, for example CO2, right? We cannot put the restricted bending method. So what we will do, and we will not be applied, will we not be able to apply the harmonic potentials. So we have two options. Either we use cosine potentials because that is defined, but then that introduce some extra potential which we don't want, because CO2 are at the lowest when they are at at the lowest energy minima when they're in a linear molecule, which this curve actually doesn't explain properly. But we can use that. We can shift this curve to 180 and then we can put another curve like this, and we can explain roughly the CO2 molecules. But there is a problem then, that sometimes it has been seen that it takes a bent, there should be this straight line of CO2, right? But if we optimize the what do you call it, if you optimize this CO2 structure with harmonic potentials and with cosine potentials, there it has been seen that the linear structure is not resolved. It's now a little bent structure. So that kind of problem comes in. So that's why people have came up with another potential, which is linear angle potential. So what is this basically? So that's not here actually. So you cannot see it from here, but it's pretty simple. So we start with another type of similar looking function, which is, there's a k term, there's half k term, right? K by 2 term, and then there is, let's look at this one. The harmonic potential is k by 2, and then there is something we are subtracting, and then square, right? So that's the basic general, what do you call, harmonic term, right? Now coming to the linear angle potential, this looks exactly same in terms of the overall function, but then how to calculate these things, because these are not theta anymore. So in the previous terms they were angles, now it is not angle. So what is it? So firstly we will look into this, which is the resting potential. Sorry, resting, sorry, I'm just mixing up names now. So this is the resting x. So what is the resting x? Is basically a multiplied by xi plus 1 minus a xk. So what is j, what is I, what is k? Now these are the three atoms that we were talking about. So oxygen is I, carbon is j, and the last one, which was k,